Experimental verification of the explosive transformation of mass defect. Researcher, Joseph George, email, atommodel@gmail.com www.youtube.com/atommodel. Introduction. The kinetic energy of product particles in nuclear reactions, such as nuclear fission, nuclear fusion, and radioactive decay, is traditionally explained through Einstein's mass energy equivalence principle, E=mc². This principle posits that the mass defect in a nuclear reaction is directly converted into energy, implying that mass and energy are interchangeable. However, my studies suggest a different explanation for the kinetic energy of product particles and fragments in such reactions. Based on this research, I propose that the mass defect in a nuclear reaction is explosively transformed into an extremely thin form of matter, and this explosion propels the reaction products. In fact, my studies indicate that the release of energy associated with a mass defect results from a change in the state of matter, rather than from the conversion of mass into energy. This hypothesis contradicts Einstein's mass energy equivalence principle. This work aims to verify this hypothesis through a novel experimental setup designed to detect and measure the kinetic energy imparted to nanoparticles placed near radioactive isotopes. By observing the behavior of these nanoparticles in a controlled environment, we can gather evidence to support the proposed mechanism of explosive transformation of the mass defect, potentially leading to a paradigm shift in our understanding of nuclear reactions. Experimental setup. Radioactive isotope selection. We will select radioactive isotopes with well-defined decay processes for this experiment. Potential candidates include uranium-238 for alpha decay and carbon-14 for beta decay. These isotopes are chosen for their well-characterized decay modes and availability. Nanoparticles, nanometer-sized particles with low interaction cross-sections for the specific type of decay products expected will be used. This minimizes the likelihood of direct collisions between decay products and nanoparticles. Vacuum chamber. The radioactive isotope and nanoparticles will be enclosed in a high vacuum chamber to reduce air resistance and prevent extraneous collisions. This controlled environment ensures that observed kinetic energies are due to decay processes rather than external factors. Particle tracker. A high-precision particle tracking system, such as a laser Doppler velocimeter or advanced high-speed cameras with nanosecond resolution, will monitor the movements of nanoparticles. This system provides accurate measurements of nanoparticle trajectories and kinetic energies. Data acquisition system. A robust data acquisition system will capture and analyze the kinetic energy and trajectories of the nanoparticles. This system ensures that all relevant data is recorded and can be thoroughly analyzed. Control setup. A control setup, identical to the experimental setup but without the radioactive isotope, will be included to account for background movements and external influences. This control helps differentiate between movements caused by decay processes and those due to other factors. Suggested improvements. Calibration and sensitivity. Calibration. The particle tracking system will be calibrated using known energy sources to ensure measurement accuracy before introducing the radioactive isotope. Sensitivity. The detection system's sensitivity will be verified to ensure it can detect minute kinetic energy changes in nanoparticles. Shielding and isolation. Electromagnetic shielding. The experiment will be shielded from external electromagnetic fields to prevent interference with particle movements. Mechanical isolation. The setup will be placed on an anti-vibration table to minimize mechanical vibrations affecting the measurements. Nanoparticles. Particles with minimal absorption or scattering cross-sections for the specific decay radiation will be used. This choice ensures that observed kinetic energies are not due to direct interaction with decay products. Background radiation monitoring. Background radiation detectors will be employed to account for any stray radiation affecting the nanoparticles. This monitoring helps isolate the effects of the radioactive decay from other radiation sources. Statistical analysis. A large dataset will be collected to apply statistical methods for analyzing nanoparticle movements, distinguishing between random fluctuations and potential evidence of explosive mass defect transformation. Redundant measurements. Redundant measurement systems, including multiple particle trackers, will be incorporated to cross-verify data and eliminate systematic errors. Environmental controls. Strict environmental controls, temperature, pressure, humidity, will be maintained to ensure they do not influence nanoparticle behavior. This consistency helps ensure that observed effects are due to the experimental variables. Experimental procedure. Setup preparation. The radioactive isotope and nanoparticles will be placed inside the vacuum chamber. All systems, particle trackers, data acquisition, will be calibrated and verified for functionality. Data collection. Nanoparticle movements will be recorded before the introduction of the radioactive isotope to establish a baseline. The radioactive isotope will be introduced, and nanoparticles will be continuously monitored. Data will be recorded over a significant period to capture sufficient decay events. Control measurements. The control setup will be run in parallel to the experimental setup, recording any spontaneous movements of nanoparticles without the isotope. Data from the experimental setup will be compared with the control to identify anomalies attributable to radioactive decay. Data analysis. The kinetic energy and trajectories of nanoparticles in both setups will be analyzed. Statistical tools will be used to identify significant deviations in kinetic energy that could indicate the influence of an explosive transformation. Verification and validation. Results will be cross-checked with theoretical predictions of kinetic energy distributions if the hypothesis holds. Repeated experiments will be conducted to ensure reproducibility of results. Conclusion. The proposed experimental setup aims to observe the kinetic energy of nanoparticles potentially influenced by the explosive transformation of the mass defect in radioactive decay. Enhancements in calibration, shielding, material selection, environmental control, and rigorous data analysis are crucial for obtaining reliable and meaningful results. These improvements ensure that the observed phenomena can be attributed with high confidence to the proposed mechanism, thereby validating the hypothesis against the established mass energy equivalence principle.